Hello there, and welcome to the Sleepy Astronaut, where curiosity drifts gently towards slumber, and science becomes your companion on the journey to peaceful rest. Tonight, we're embarking on a tranquil voyage through the vast cosmos to explore one of humanity's most remarkable achievements: how spacecraft travel through the endless expanse of space. It's a tale of physics, poetry, and the quiet dance of objects moving through the void, guided by forces both invisible and eternal. But before we launch into this soothing exploration of rocket engines, orbital mechanics, and the delicate choreography of celestial navigation, I'd love to know where in the world you're listening from tonight. And as you settle in, perhaps you can imagine yourself as a gentle traveler, aboard your own spacecraft, drifting peacefully through the star-filled darkness. If you find this cosmic journey calming, or perhaps learn something that sparks your curiosity in the most relaxing way possible, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of scientific serenity reach other stargazers who might need a peaceful pause in their evening too. Now, I do hope this isn't so fascinating that it keeps you wide awake. But if it does, well, at least you'll drift off, knowing a bit more about how we humans have learned to dance with gravity and glide through the infinite. So settle back into your most comfortable position, slow your breathing, and let's begin our gentle exploration. Because somewhere between the roar of rocket engines and the whispered silence of orbital mechanics is the beautiful story of how spacecraft travel through space. Space, as we know it, is not quite the empty void it might appear to be from our earthbound perspective. It's a realm where familiar rules of motion take on an almost dreamlike quality, where the simple act of moving forward becomes an elegant interplay between physics and poetry. When we think about how things move here on Earth, we're accustomed to friction, wind resistance, and the need for continuous effort to maintain motion. A car needs its engine running to keep moving. A bicycle rider must keep pedaling, and even a paper airplane eventually succumbs to air resistance and gravity. But space. Oh, space is wonderfully different. It's a place where Newton's first law of motion reigns supreme with an almost magical simplicity. An object in motion stays in motion unless acted upon by an external force. And in the near vacuum of space, there's precious little to slow things down. This fundamental difference creates a realm where spacecraft can coast for months or even years without firing their engines, gliding silently through the cosmic dark like celestial sailing ships, riding invisible currents of gravitational influence. It's a place where the tiniest push can send something on a journey lasting decades, where a spacecraft launched decades ago continues its patient trek toward the outer reaches of our solar system, powered not by fuel, but by the momentum imparted so long ago and the gentle gravitational nudges of planets it encounters along the way. But how do we get these mechanical explorers moving in the first place? How do we give them that initial push that sends them on their cosmic wanderings? The answer lies in one of the most elemental principles of physics. Newton's third law: for every action, there is an equal and opposite reaction. It's the same principle that makes a balloon zoom around the room when you let go of its neck, or causes you to feel pushed back into your seat when a car accelerates forward. And it's the beating heart of every rocket that has ever lifted off from Earth. Imagine for a moment the simplest demonstration of this principle. You're standing on a perfectly smooth, frozen pond, wearing ice skates and holding a heavy ball. If you throw that ball as hard as you can in one direction, you'll find yourself gliding backward in the opposite direction. The harder you throw the ball, the faster you'll glide backward. This happens because momentum must be conserved. The momentum you give to the ball must be balanced by an equal and opposite momentum imparted to you. This is exactly how rockets work in the vacuum of space. Except instead of throwing balls, they're expelling hot gases at tremendous speeds. A rocket engine is essentially a very sophisticated way of throwing mass in one direction to push the spacecraft in the other. The beauty of this system lies in its self-contained nature, unlike a car which needs air to mix with its fuel, or a propeller which needs air to push against a rocket, carries everything it needs, both the fuel and the oxidizer that allows that fuel to burn. This makes rockets uniquely suited for space travel, where there's no air to breathe or push against. The most common type of spacecraft propulsion is chemical propulsion, the same basic technology that has been launching rockets since the early days of spaceflight. These systems work by combining fuel with an oxidizer in a combustion chamber, creating a controlled explosion that produces extremely hot gases. These gases then rush out through a carefully designed nozzle at tremendous speeds, often exceeding several kilometers per second. The nozzle shape is crucial as it converts the thermal energy of those hot combustion gases into kinetic energy, accelerating them to the highest possible speeds. Think of it like a controlled volcanic eruption happening thousands of times per second. The expanding gases want to go in all directions, but the combustion chamber and nozzle channel all that explosive energy in precisely the direction you want, creating thrust that pushes the spacecraft in the opposite direction. The more mass you can expel, and the faster you can expel it, the more thrust you generate. It's an elegant dance between chemistry, physics, and engineering. Liquid rocket engines represent the pinnacle of chemical propulsion technology, offering the ability to start-stop and throttle the engine as needed. They store fuel and oxidizer in separate tanks, then pump them into the combustion chamber, where they mix and ignite. Some of the most powerful combinations include liquid hydrogen with liquid oxygen, which burns incredibly hot and produces water vapor as its exhaust, or kerosene with liquid oxygen, which provides denser thrust ideal for lifting heavy payloads off planetary surfaces. These engines can generate tremendous amounts of thrust, enough to overcome Earth's gravity and accelerate massive spacecraft to the speeds needed for interplanetary travel. Solid rocket engines take a different approach, mixing fuel and oxidizer into a solid mixture that's packed into a cylindrical casing. Once ignited, they burn like a very energetic candle, producing steady thrust until all the propellant is consumed, while they can't be throttled or shut down once started. They're simpler, more reliable, and can produce enormous amounts of thrust, making them popular for initial launch phases and emergency systems. The Space Shuttle's solid rocket boosters were magnificent examples, capable of producing over 3 million pounds of thrust each. But here's where space travel becomes truly fascinating, once a spacecraft has escaped the gravitational embrace of its home planet and achieved the speeds necessary for interplanetary travel. Chemical rockets, while powerful, become somewhat inefficient for the long haul. They consume enormous amounts of propellant to generate their thrust, and carrying enough fuel for extended missions becomes a significant challenge. Imagine trying to drive across a continent but having to carry all the gasoline your car would ever need in the trunk. It quickly becomes impractical. This is where electric propulsion enters our story, like a gentle whisper compared to the roar of chemical rockets. These systems represent one of the most elegant solutions to long-duration space travel ever devised, instead of creating thrust through explosive combustion. They use electrical energy to accelerate tiny amounts of propellant to extraordinary speeds that would make the exhaust from chemical rockets seem sluggish by comparison. Electric propulsion systems work on the same fundamental principle as chemical rockets. They expel mass in one direction to create thrust in the other, but they do so with an almost ethereal efficiency. Instead of burning fuel, they use electricity, often generated by solar panels, to accelerate propellant particles to velocities that can exceed 30 kilometers per second. That's nearly 100 times faster than the speed of sound and far faster than any chemical rocket could ever achieve. The most common type of electric propulsion is the ion engine, a device that sounds like it belongs in science fiction, but has become a reliable workhorse for deep space missions. These engines work by stripping electrons from atoms of propellant, usually the noble gas xenon, creating positively charged ions. These ions are then accelerated through an electric field, reaching tremendous speeds before being expelled from the spacecraft. The result is thrust so gentle you could barely feel it if you held the engine in your hand. Yet this whisper-soft push can operate continuously for months or years, gradually building up enormous velocities. The Deep Space One mission launched in 1998 provided a beautiful demonstration of ion propulsion in action. This small spacecraft carried an experimental xenon ion engine that produced thrust equivalent to the weight of a piece of paper resting on your palm, yet over the course of its mission. This gentle push accumulated over 16,000 hours of operation, consuming only 81.5 kilograms of xenon, while providing the spacecraft with enough velocity change to visit both an asteroid and a comet, something that would have been impossible with chemical propulsion alone. The elegance of ion propulsion lies not just in its efficiency, but in its almost meditative approach to space travel, where chemical rockets deliver their energy in dramatic bursts lasting minutes. Ion engines whisper their spacecraft forward, with the patience of glaciers carving valleys over millennia. The thrust they produce is so gentle that, if you were floating beside the spacecraft, you might not even notice the acceleration. Yet this barely perceptible push accumulates over time like compound interest, building velocities that chemical rockets could never achieve without consuming impossibly large amounts of fuel. There are other forms of electric propulsion, each with their own quiet poetry hall. Effect thrusters trap electrons in magnetic fields while accelerating ions through electric fields, creating a more compact design that has become popular for commercial satellites. These engines glow with an ethereal blue light as they operate their plasma exhaust, creating an almost supernatural appearance as they push spacecraft through the darkness. Magnetoplasma dynamic thrusters use magnetic fields to accelerate plasma currents, achieving even higher power levels, though they remain largely experimental, representing the cutting edge of propulsion research. But propulsion is only half the story of how spacecraft travel through space. Equally important is understanding the invisible highways and byways that govern motion in the cosmic realm. This is the domain of orbital mechanics, a field of physics that reveals the hidden choreography underlying all space travel. It's a realm where intuition often fails us, where speeding up can actually slow you down, and where the shortest path between 2 points is rarely a straight line. Orbital mechanics is founded on the same principles that govern the motion of planets around the Sun, the dance of moons around their parent worlds, and the graceful arcs of comets as they sweep through the solar system. At its heart lies the concept that any object moving through a gravitational field will follow a path described by one of the conic sections, those elegant mathematical curves that include circles, ellipses, parabolas, and hyperbolas. The shape of the path depends entirely on the object's speed and the strength of the gravitational field it encounters. Circular orbits represent the simplest case where a spacecraft moves at exactly the right speed to maintain a constant distance from the central body. It's a delicate balance between the spacecraft's tendency to fly off in a straight line and gravity's relentless pull inward like a ball on a string. Being swung in a perfect circle, the centripetal force provided by gravity exactly balances the centrifugal force trying to pull the spacecraft outward. Most artificial satellites around Earth follow nearly circular orbits because they provide predictable coverage patterns and relatively simple maintenance requirements. Elliptical orbits are far more common in nature and offer spacecraft designers tremendous flexibility. These elongated paths have a closest approach called periapsis and a farthest point called apoapsis. The spacecraft moves fastest when closest to the central body and slowest when farthest away. Following Kepler's laws with mathematical precision, the International Space Station follows a slightly elliptical orbit around Earth, while most interplanetary missions use highly elliptical trajectories that stretch across millions of kilometers of space. The counterintuitive nature of orbital mechanics becomes apparent when you consider how spacecraft change their orbits. If two spacecraft are in the same circular orbit and the trailing one wants to catch up with the leader, you might think the solution is simply to fire engines forward to speed up. But this actually makes the problem worse. Adding energy to a circular orbit doesn't make you go faster around the same circle. Instead, it lifts you to a higher orbit, where according to Kepler's laws, you actually move more slowly. The trailing spacecraft ends up falling further behind, despite using fuel to speed up. To actually catch up, the trailing spacecraft must first slow down, dropping to a lower orbit, where it will move faster than the target. Once it has gained some ground in this lower, faster orbit, it can then raise its orbit back up to meet the target. This complex dance of orbital rendezvous requires multiple precisely timed engine burns, often taking hours or days to complete. It's like trying to merge onto a highway where speeding up moves you to a slower lane and slowing down moves you to a faster one. The mathematics of orbital mechanics reveal that all bound orbits, whether circular or elliptical, have periods that depend only on their average distance from the central body. This relationship, discovered by Johannes Kepler 4 centuries ago, means that spacecraft in higher orbits always take longer to complete one revolution than those in lower orbits. It's why geostationary satellites orbiting at 36,000 kilometers altitude take exactly 24 hours to orbit Earth, matching our planet's rotation, while the International Space Station at 400 kilometers altitude whips around the globe every 90 minutes. For interplanetary travel, spacecraft must follow trajectories that escape the gravitational bonds of their home planet entirely. These hyperbolic escape trajectories require the spacecraft to achieve what's called escape velocity, the minimum speed needed to break free from a planet's gravitational influence for Earth. This magic number is about 11 kilometers per second, though the exact value depends on altitude and the specific trajectory chosen. Once a spacecraft achieves escape velocity, it's free to coast through interplanetary space following the gravitational influence of the Sun. The most energy-efficient way to travel between planets is the Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it in 1902. This elegant trajectory uses exactly 2 engine burns, one to leave the departure planet's orbit and another to enter the destination planet's orbit. The spacecraft follows an elliptical path around the Sun that touches both planetary orbits, like drawing a tangent line between 2 circles. A Hohmann transfer to Mars begins when Earth and Mars are positioned so that Mars will be at the right place. When the spacecraft arrives approximately 7 months later, the spacecraft is accelerated beyond Earth's escape velocity, placing it in a solar orbit with its closest point at Earth's distance from the Sun and its farthest point at Mars's distance. The timing must be precise because both the spacecraft and Mars must arrive at the same point in space simultaneously. This celestial rendezvous requires calculations accurate to within minutes after a journey lasting months. The Mars Pathfinder mission, launched in 1996, exemplified this principle, perfectly departing Earth when the planetary alignment was optimal and following a classic Hohmann transfer trajectory that carried it 500 million kilometers through space over 7 months. Despite the vast distance traveled, the spacecraft needed only minor course corrections along the way, demonstrating the predictable elegance of orbital mechanics. When Pathfinder arrived at Mars on July 4, 1997, it had to slow down enough for the planet's gravity to capture it into orbit, then deploy its revolutionary airbag landing system to bounce safely onto the Martian surface. The beauty of Hohmann transfers lies not just in their efficiency, but in their timing. These launch windows, when the planets align favorably, occur roughly every 26 months for Mars missions, creating a rhythm that governs our exploration of the red planet like a cosmic metronome. Spacecraft must wait patiently for these celestial appointments, when the dance of orbital mechanics brings departure and destination into perfect alignment. Missing a launch window means waiting over 2 years for the next opportunity, a reminder that even our most advanced technology must bow to the ancient rhythms of planetary motion. But what if you need to travel faster than a Hohmann transfer allows? What if mission requirements demand arrival times that can't wait for the leisurely pace of minimum energy trajectories? This is where higher energy transfers come into play, requiring more fuel, but offering shorter travel times. These trajectories follow more eccentric ellipses that arc higher above or dive deeper below the plane of planetary orbits, trading fuel efficiency for speed, like choosing between a scenic coastal highway and a direct interstate route. The mathematics of these transfers reveal fascinating insights about the relationship between energy, time, and distance in space. Adding just a little more energy to a Hohmann transfer can reduce travel time significantly, but there's a point of diminishing returns where additional energy produces smaller and smaller time savings. Eventually, you reach trajectories that are nearly parabolic, requiring enormous amounts of energy for only modest improvements in travel time. It's a delicate optimization problem that mission planners must solve, balancing the constraints of fuel mass launch windows and arrival requirements. Spacecraft navigating these interplanetary highways face unique challenges that have no earthly equivalent. They must account for the gravitational influences of multiple bodies simultaneously as they transition from Earth's sphere of influence to the Sun's domain, then eventually to their destination planet's gravitational embrace. This complex multi-body problem requires sophisticated mathematical techniques and computational power to solve accurately. Yet the underlying principles remain elegantly simple objects in space, follow predictable paths governed by the fundamental forces of nature. The patched conic approximation provides a practical way to handle these complex trajectories by dividing the journey into segments where one gravitational body dominates the spacecraft's motion. During launch and early flight, Earth's gravity controls the trajectory until the spacecraft reaches a distance where the Sun's influence becomes paramount. Then, for most of the interplanetary cruise phase, solar gravity dominates until the spacecraft approaches its destination, where the target planet's gravity takes over. It's like following different roadmaps for different portions of a long journey, each valid in its own region, but requiring careful transitions between them. This segmented approach allows mission planners to design trajectories using well-understood two-body orbital mechanics techniques while still accounting for the major gravitational influences throughout the journey. The result is a patchwork of conic sections, ellipses around Earth transitioning to hyperbolic escape trajectories, then elliptical solar orbits, and finally, hyperbolic approach trajectories. At the destination, each piece perfectly calculated to connect smoothly with the next. Some of the most elegant demonstrations of orbital mechanics come from gravity assist maneuvers where spacecraft use the motion of planets themselves to gain or lose energy. These cosmic slingshots allow missions to reach destinations that would otherwise be impossible with conventional propulsion. The Voyager spacecraft, launched in the 1970s, used a rare alignment of the outer planets to hopscotch, from Jupiter to Saturn to Uranus and Neptune, gaining speed at each encounter like a ball bouncing off the front of a moving train. The physics behind gravity assists reveals the subtle interplay between reference frames and conservation of momentum. From the planet's perspective, the spacecraft approaches, gains speed as it falls into the gravitational well, then loses that same speed as it climbs back out, arriving with the same speed it started with. But from the Sun's perspective, the spacecraft has gained orbital energy by stealing a tiny amount of the planet's orbital motion around the Sun. The planet's enormous mass means this theft is imperceptible. But for the lightweight spacecraft, the energy gain can be enormous. These maneuvers require exquisite precision in both timing and trajectory. A spacecraft approaching Jupiter for a gravity assist must arrive at exactly the right place at exactly the right time, with exactly the right velocity vector. Even small errors can send the spacecraft careening off course, or worse, into a collision trajectory with the planet. The Cassini mission to Saturn used multiple gravity assists at Venus, Earth, and Jupiter, building up enough speed to reach the outer solar system, while carrying the heavy Huygens probe that would eventually land on Titan. The psychological challenge of gravity assists lies in their counterintuitive nature. Mission controllers must aim their spacecraft not at where the planet is, but at where it will be, accounting for the complex orbital dance of multiple bodies. Over periods of months or years, it requires a kind of cosmic billiards, where you're shooting at moving targets, while riding on another moving platform, using the motion of one ball to redirect another, in a game played across astronomical distances. Modern spacecraft employ increasingly sophisticated techniques for orbital maneuvering, using combinations of chemical and electric propulsion to optimize their trajectories. The Dawn mission, launched in 2007, used ion propulsion to visit both the asteroid Vesta and the dwarf planet. Ceres, something impossible. With chemical rockets alone, the gentle but persistent thrust of its ion engines allowed it to spiral slowly outward from Earth's orbit, enter orbit around Vesta, study the asteroid for over a year, then depart and travel to Ceres, where it became the first spacecraft to orbit a dwarf planet. This mission demonstrated the unique capabilities of electric propulsion for complex multi-target missions, where chemical rockets would have required prohibitively large amounts of fuel. Dawn's ion engines operated for over 11 years, accumulating more than 57,000 hours of thrust time while consuming only 425 kilograms of xenon propellant. The equivalent performance with chemical rockets would have required thousands of kilograms of propellant, making the mission impossible within reasonable mass and cost constraints. The future of spacecraft propulsion promises even more exotic possibilities. Nuclear thermal rockets could provide the high thrust of chemical systems with much better fuel efficiency by using a nuclear reactor to heat propellant to extreme temperatures. Solar sails could harness the gentle pressure of sunlight itself for propulsion, requiring no propellant at all, just vast gossamer sheets that catch photons like wind in a sail. These systems could enable missions of unprecedented scope and duration, limited only by the mechanical lifetime of the spacecraft components. Fusion rockets represent the holy grail of space propulsion, potentially offering both high thrust and extraordinary fuel efficiency by harnessing the same nuclear reactions that power the Sun. These systems could reduce travel times to the outer planets from years to months and make interstellar missions feasible within human lifetimes. Though the technical challenges of controlled fusion in space remain formidable, the physics is sound and research continues toward making these systems practical. Each advancement in propulsion technology opens new possibilities for exploration, allowing us to reach destinations previously beyond our grasp and to study the solar system with ever greater detail and precision, from the first chemical rockets that barely escaped Earth's atmosphere to ion engines that whisper spacecraft across billions of kilometers of space, to future fusion rockets that might carry humans to the stars. The story of spacecraft propulsion is one of constantly expanding horizons and growing understanding of our place in the cosmos. As we've journeyed through this gentle exploration of how spacecraft travel through space, we've seen how the marriage of propulsion technology and orbital mechanics creates the foundation for all space exploration, from the thunderous roar of launch vehicles lifting off from Earth to the silent efficiency of ion engines pushing robotic explorers toward distant worlds. Each mission represents a triumph of human ingenuity and our endless curiosity about the universe around us. The elegance of spacecraft navigation extends far beyond simply pointing in the right direction and firing engines. It involves a delicate choreography of timing, precision, and patience that unfolds across the vast theater of space. When mission controllers plot a course to Mars or Jupiter, they're not just calculating distances and velocities. They're orchestrating a cosmic ballet where every participant must arrive at precisely the right place at exactly the right moment, like conducting a symphony where the musicians are scattered across light years and the tempo is measured in months rather than beats. Consider for a moment the extraordinary precision required for these interplanetary rendezvous. The New Horizons mission, launched toward Pluto in 2006, had to travel over 9 years and cover more than 5 billion kilometers to arrive within a few thousand kilometers of a world smaller than our own moon. The spacecraft's trajectory was calculated so precisely that after nearly a decade of flight, It passed through a narrow corridor of space just 30 kilometers wide relative to Pluto's position. This level of accuracy is equivalent to hitting a golf ball from New York and having it land in a specific teacup in Los Angeles after bouncing off buildings and streetlights along the way. The psychological demands of such missions stretch human patience and planning to their limits. Engineers must design spacecraft that will operate reliably for years or decades in an environment where repair is impossible, and communication delays can stretch to hours. Mission planners must anticipate problems that might not arise for years, and build solutions into systems that must work flawlessly when their moment comes. It's like preparing for an exam that won't be given for a decade, but will test every aspect of your knowledge and preparation. Yet perhaps the most beautiful aspect of spacecraft navigation lies in its fundamental simplicity. Beneath all the complex calculations and sophisticated equipment, the basic principles remain elegantly straightforward objects in motion. Stay in motion. Gravity provides the invisible rails along which spacecraft glide, and every action produces an equal and opposite reaction. These simple truths, discovered centuries ago by brilliant minds, continue to guide our mechanical emissaries as they explore the furthest reaches of our solar system. The Voyager spacecraft, launched in 1977, continue their journey into interstellar space more than 4 decades after leaving Earth, powered by the momentum imparted during their launch and the gravitational assists they received from the giant planets they encountered along the way. These elderly explorers now drift through the space between stars, carrying messages from Earth on golden records like bottles cast into an infinite ocean. Their continued operation represents one of humanity's greatest achievements in engineering and exploration. Modern missions employ increasingly sophisticated combinations of propulsion systems to optimize their capabilities. The Europa Clipper missions scheduled to explore Jupiter's ice-covered moon will use both chemical and electric propulsion during its journey. Chemical rockets will provide the high thrust needed for major maneuvers, while ion engines will make fine adjustments and maintain the spacecraft's trajectory over the long cruise to Jupiter. This hybrid approach represents the evolution of spacecraft design towards systems that can adapt their propulsion methods to the specific requirements of each phase of their mission. The challenges of deep space navigation extend beyond simply getting spacecraft to their destinations. They must also be able to operate autonomously for extended periods, making critical decisions without the benefit of real-time communication with Earth. When the Perseverance rover lands on Mars, mission controllers on Earth won't know the outcome for over 11 minutes due to the speed of light. Delay during those crucial moments of descent. The spacecraft must rely entirely on its own sensors and programming to navigate safely to the surface. This autonomy requirement drives spacecraft designers to create systems that can think for themselves to some degree, using artificial intelligence and machine learning algorithms to recognize and respond to unexpected situations. The Deep Space One mission we explored earlier was one of the first to demonstrate autonomous navigation, where the spacecraft used its own sensors to track asteroids and adjust its trajectory without waiting for instructions from Earth. This capability has become increasingly important as missions venture to more distant destinations, where communication delays make real-time control impossible. The future of spacecraft navigation promises even more remarkable capabilities. Missions are being planned that will use swarms of small spacecraft working together to explore multiple targets. Simultaneously, these distributed missions could provide unprecedented coverage of planetary systems, allowing us to study the complex interactions between planets' moons and space environments in ways that single spacecraft never could imagine. A fleet of tiny explorers spreading out across the Jovian system, each one studying different aspects of Jupiter's magnetosphere, while maintaining communication with the others to coordinate their observations. Propulsion technology continues to evolve toward ever more efficient and capable systems. Breakthrough Starshot, an ambitious project to send tiny spacecraft to the nearest star system, proposes using powerful laser beams to accelerate postage stamp-sized spacecraft to 20% the speed of light. Such craft could reach Proxima Centauri in just 20 years, carrying miniaturized instruments to photograph and study planets orbiting our nearest stellar neighbour. Though the technical challenges are enormous, the basic physics is sound, representing a possible path toward true interstellar exploration. The psychological impact of these missions extends far beyond their scientific value. They represent humanity's drive to explore and understand our place in the universe. Each spacecraft that ventures into the cosmic deep carries with it our curiosity, our ingenuity, and our hope for discovery. When we receive images from Mars or Saturn, or the edge of the solar system, we're seeing through mechanical eyes that extend our vision across impossible distances. These robotic ambassadors become extensions of ourselves, allowing us to touch worlds we may never visit in person. The meditation on spacecraft travel reveals something profound about the nature of exploration itself. It requires patience, vision, and the willingness to commit resources to endeavors whose payoffs may not be realized for years or decades. The engineers who designed the Voyager spacecraft in the 1970s could never have imagined that their creations would still be sending data home 45 years later. Yet their careful work and attention to detail created systems robust enough to operate far longer than anyone dared hope. This long-term perspective stands in stark contrast to our increasingly fast-paced world, where instant gratification and immediate results are often expected. Space exploration operates on geological timescales, where success is measured not in quarters or years, but in decades and centuries. The Hubble Space Telescope has been observing the universe for over 3 decades, revealing cosmic phenomena that unfold over millions of years. The James Webb Space Telescope now peers even deeper into space and time, showing us galaxies as they appeared when the universe was young. The relationship between spacecraft and their human creators evolves over the course of long missions. What begins as a purely mechanical relationship between operator and machine often develops into something more personal. Mission controllers speak of their spacecraft as though they were beloved pets or family members, celebrating their successes and mourning their failures. When contact is lost, the Opportunity rover on Mars operated for nearly 15 years, far exceeding its planned 90-day mission, when a dust storm finally ended its mission in 2018. The last message it sent was interpreted as roughly equivalent to, "My battery is low and it's getting dark," prompting an outpouring of emotion from people around the world who had followed its adventures. These emotional connections reveal something important about human nature and our relationship with exploration. We invest these mechanical travelers with aspects of ourselves, seeing in their journeys reflections of our own desire to explore and discover. When a spacecraft successfully completes a difficult maneuver or captures a stunning image, we share in its triumph when technical problems threaten a mission. We worry about its fate as though it were a friend in danger. This anthropomorphization of spacecraft helps us connect emotionally with endeavors that might otherwise seem coldly technical. The environmental challenges faced by spacecraft in the deep reaches of space would be instantly lethal to any living creature. Temperatures that swing from hundreds of degrees above absolute zero to hundreds of degrees below radiation levels that would cook biological tissue in minutes, and the complete absence of air, water, or any of the substances that life requires. Yet our mechanical emissaries thrive in these conditions, powered by sunlight or radioactive decay, communicating across billions of kilometers and operating with a reliability that often exceeds that of Earthbound systems. This resilience comes from careful engineering and redundant systems designed to continue operating even when individual components fail. Spacecraft carry backup computers, backup communication systems, and backup power sources. Every critical function has multiple ways to be accomplished, because failure in deep space means the end of the mission. The Mars Curiosity rover carries 6 separate computer systems that can take over primary control if needed, and multiple ways to communicate with Earth, ensuring that even significant hardware failures won't necessarily end the mission. The data transmission challenges of deep space missions require remarkable feats of engineering and patience. Signals from Voyager 1, now in interstellar space, take over 22 hours to reach Earth and arrive with a strength billions of times weaker than the power of a digital watch battery. Yet sophisticated antennas and signal processing techniques can extract meaningful data from these whispers across the cosmic void. The Deep Space Network, with giant antennas in California, Spain, and Australia, maintains constant contact with our distant explorers, ensuring that their discoveries can be shared with the world. As spacecraft venture ever farther from home, the delays in communication create unique operational challenges that don't exist for Earthbound systems. When the Cassini spacecraft was exploring Saturn, any command sent from Earth took over an hour to reach the spacecraft and another hour for confirmation to return during critical events like close flybys of Saturn's moons. The spacecraft had to operate autonomously, following pre-programmed sequences. Because real-time control was impossible, this delay forces mission planners to think far ahead, anticipating every possible scenario and programming responses for situations that may never occur. The philosophical implications of spacecraft travel extend beyond the technical achievements to questions about humanity's place in the universe and our destiny as a species. These mechanical explorers serve as our ambassadors to the cosmos, carrying not just scientific instruments, but messages about who we are and what we value. The golden records on the Voyager spacecraft contain music, art, and greetings from Earth, intended for any intelligent beings who might someday encounter them, though the chances of such contact are vanishingly small. The gesture represents hope that we are not alone in the universe. The images returned by spacecraft have fundamentally changed our perspective on Earth and our place in the cosmos. The pale blue dot photograph taken by Voyager 1 from the edge of the solar system shows Earth as a tiny speck suspended in a sunbeam, highlighting both our cosmic insignificance and the precious uniqueness of our world. These views from space have inspired environmental awareness and a sense of global unity that transcends national boundaries, reminding us that we all share this small oasis in the vast darkness. Spacecraft missions also serve as time capsules, preserving human knowledge and achievement for future generations. The lunar modules left on the Moon by the Apollo missions will remain there for millions of years, barring asteroid impacts, serving as monuments to human ingenuity and courage. The plaques and instruments left by various landers on Mars will someday be archaeological artifacts for future explorers, whether human or robotic, telling the story of our first tentative steps toward becoming a spacefaring civilization. The collaboration required for spacecraft missions brings together people from around the world in pursuit of common goals, transcending political and cultural boundaries. The International Space Station represents perhaps the finest example of such cooperation, with former adversaries working together to push the boundaries of human knowledge and capability. These partnerships demonstrate that our greatest achievements often come when we set aside our differences and work toward shared objectives. The economic benefits of spacecraft missions extend far beyond their scientific value. The technologies developed for space exploration often find applications in everyday life, from miniaturized electronics to advanced materials to life support systems. Innovations driven by the extreme requirements of space travel frequently revolutionize terrestrial industries in unexpected ways. The global positioning system that now guides everything from smartphones to delivery trucks grew out of military satellites that themselves were descendants of early space exploration efforts. The inspirational value of spacecraft missions cannot be quantified, but may be their most important contribution to human society. Children who watch rovers explore Mars or see images of distant galaxies may be inspired to pursue careers in science, engineering, or exploration. Adults who follow these missions often report a renewed sense of wonder about the universe and our place within it. This inspiration drives the next generation of explorers and innovators, ensuring that the journey of discovery continues. As we drift gently through this exploration of how spacecraft travel through space, we begin to appreciate the profound beauty underlying these mechanical journeys. It's not just about rockets and orbits, but about humanity's endless curiosity and our determination to reach beyond the comfortable confines of our home world. Each spacecraft that ventures into the cosmic deep carries with it a piece of our collective spirit, our dreams of discovery, and our hope that somewhere in the vast universe we might find answers to the deepest questions about existence itself. And as these tireless explorers continue their patient journeys through the darkness, they remind us that the greatest adventures often unfold, not with dramatic flourishes, but with quiet persistence, gentle nudges, and the steady accumular, tine of knowledge across the vast expanses of space and time. The story of spacecraft navigation reveals itself to be far more nuanced than simply pointing and shooting across the void. It's a delicate art of prediction and patience, where mission planners must think like cosmic chess masters, considering moves that won't pay off for years or even decades. When the New Horizons spacecraft was launched toward Pluto in 2006, its controllers had to account not just for where Pluto would be 9 years in the future, but for how the spacecraft's own journey would be affected by the gravitational tugs of every significant body it encountered along the way, like plotting a course through a three-dimensional maze where all the walls are slowly moving. This predictive challenge becomes even more fascinating when you consider gravitational slingshots, those elegant cosmic billiard shots where spacecraft borrow energy from the orbital motion of planets themselves. The Cassini mission to Saturn performed 7 of these gravity assists using Venus twice, Earth once, and Jupiter once, to build up the tremendous velocity needed to reach the outer solar system. Each encounter had to be timed with extraordinary precision, arriving at exactly the right place, at exactly the right moment, to receive the perfect gravitational nudge in the right direction. Imagine trying to catch a series of moving trains while riding on another moving train, where each successful catch propels you faster toward your ultimate destination. But missing any one of them means your journey becomes impossible. That's the delicate choreography of interplanetary navigation, where spacecraft must thread through narrow corridors of space and time, with margins for error measured in kilometers and minutes after journeys lasting years. The Voyager Grand Tour missions, launched in the 1970s, represent perhaps the most ambitious navigation challenge ever attempted, taking advantage of a rare alignment of the outer planets that occurs only once every 176 years. These twin spacecraft hopscotched from Jupiter to Saturn and beyond, using the gravitational energy of each giant planet to accelerate toward the next like stones skipping across a cosmic pond. Each bounce carefully calculated to maximize the scientific return while conserving precious fuel. But the beauty of spacecraft navigation extends beyond these dramatic planetary encounters to the quiet elegance of station keeping and orbital maintenance. The Hubble Space Telescope has spent over 3 decades in Earth orbit, requiring periodic adjustments to counteract atmospheric drag and maintain its precise pointing. The International Space Station needs regular boosts to prevent it from gradually spiraling back to Earth as the tenuous upper atmosphere slowly saps its orbital energy. These maintenance maneuvers require the same fundamental principles as interplanetary travel, just applied with surgical precision to keep valuable assets exactly where they need to be. The psychological dimension of long-duration missions creates unique challenges that ground-based operations never face. Imagine designing a system that must work perfectly years in the future, with no possibility of hands-on repair or real-time troubleshooting. The Mars rovers exemplify this challenge, operating on a world where radio signals take between 4 and 24 minutes to travel each way, depending on planetary positions during critical operations like landing or navigating dangerous terrain. The spacecraft must make life or death decisions completely autonomously, trusting in programming written years earlier by engineers who could only imagine the challenges their mechanical children might face. This autonomy requirement has driven remarkable advances in artificial intelligence and machine learning applied to spacecraft systems. The Mars helicopter Ingenuity demonstrated autonomous flight on another world, making split-second decisions about navigation and obstacle avoidance. Without any possibility of real-time human intervention, its success opened new possibilities for aerial exploration of planets and moons, where the thin atmospheres make flight challenging but not impossible. The communication challenges of deep space missions create their own poetry of patience and precision. The Voyager spacecraft, now beyond the heliopause in interstellar space, transmit their data with radio signals weaker than the energy of a snowflake hitting the ground. Yet the deep space network with its massive dish antennas can still decode these whispers from the edge of our solar system, extracting meaningful scientific data from signals that have traveled for over 20 hours across billions of kilometers of space. Mission controllers speak of their distant spacecraft with an almost parental affection, celebrating successful maneuvers and worrying during communication blackouts, when spacecraft pass behind planets or point their antennas away from Earth. These emotional connections develop over years of daily interaction as controllers monitor spacecraft health, adjust trajectories, and troubleshoot problems across the vast emptiness. The Opportunity rover on Mars operated for nearly 15 years, far beyond its planned 90-day mission. And when dust storms finally ended its mission, the last transmission was poetically interpreted as equivalent to, "My battery is low and it's getting dark." The engineering philosophy behind spacecraft design reflects a deep understanding of the unforgiving nature of space, where second chances don't exist. Redundancy becomes not just important, but essential. Every critical system has backups, and the backups have backups. The Mars Curiosity rover carries 6 separate computer systems, any one of which can control the entire vehicle. Multiple communication systems ensure that even if primary antennas fail, the spacecraft can still phone home, and fault protection software constantly monitors all systems, ready to switch to safe modes if problems are detected. Thermal management represents one of the most challenging aspects of spacecraft design in the vacuum of space, where there's no air to carry heat away. Spacecraft must rely entirely on radiation to shed excess thermal energy, while simultaneously protecting sensitive electronics from temperature extremes that can swing from hundreds of degrees above absolute zero in direct sunlight to hundreds of degrees below. In shadow radiators, heat pipes and multi-layer insulation blankets work together like a spacecraft's cardiovascular system, circulating and regulating thermal energy to keep everything at optimal operating temperatures. The precision required for spacecraft navigation would be impressive enough if it involved only predictable orbital mechanics. But space is filled with subtle influences that can gradually affect trajectories over time. Solar radiation pressure pushes gently, but persistently, on spacecraft surfaces like a cosmic wind. The gravitational influence of asteroids and comets creates tiny perturbations in trajectories and even the shape of planets themselves slightly non-spherical, due to rotation affects orbital mechanics in ways that must be accounted for in long-term mission planning. These minute forces accumulate over time like compound interest, gradually shifting spacecraft trajectories in ways that could spell the difference between mission success and failure. The Deep Space Network regularly measures spacecraft positions with extraordinary precision, using radio signals to determine locations accurate to within a few kilometers across distances of billions of kilometers. This information feeds into sophisticated computer models that predict future positions and calculate the tiny course corrections needed to keep missions on track. The software that controls modern spacecraft represents some of the most reliable code ever written, where a single bug could end a billion-dollar mission. Years of development testing and verification go into every line of code, with multiple independent teams checking and rechecking every algorithm. Formal verification methods borrowed from mathematics prove that critical software components will behave correctly under all possible conditions, and extensive simulation testing subjects the software to millions of scenarios it might encounter during its mission. Spacecraft power systems must operate reliably for years or decades. Far from any maintenance, the Mars rovers use radioisotope thermoelectric generators that convert the heat from radioactive decay into electricity, providing steady power for decades without any moving parts. Solar panels on spacecraft bound for the outer solar system must be enormous to capture enough of the dim sunlight available at those distances, while those exploring the inner solar system must withstand intense radiation that would quickly damage Earthbound solar installations. The data storage and transmission systems on spacecraft face unique challenges managing years' worth of scientific observations while operating under strict power and bandwidth constraints. Spacecraft often must choose which data to keep and which to discard, based on scientific priority algorithms written into their programming, like digital librarians deciding which books are worth preserving for future generations. Compression techniques squeeze maximum information into minimum bandwidth, while error correction codes ensure that data corrupted by cosmic radiation can be reconstructed perfectly on Earth. The miniaturization of spacecraft technology has opened new possibilities for exploration that were unimaginable just decades ago. Cubes, at no larger than bread loaves, now carry sophisticated instruments to study Earth's atmosphere and magnetic field. Swarms of tiny spacecraft could someday explore the moons of Jupiter, simultaneously providing coverage, impossible with traditional large spacecraft. The breakthrough Starshot initiative proposes spacecraft, no larger than postage stamps accelerated by powerful lasers to 20% the speed of light, potentially reaching the nearest star system within our lifetimes. But perhaps the most remarkable aspect of spacecraft design is how these mechanical systems embody human values and aspirations. The golden records carried by the Voyager spacecraft contain music art and messages from Earth intended for any intelligent beings who might someday encounter them, though the probability of such contact is vanishingly small. The gesture represents hope that we are not alone in the universe, and that our creations might someday serve as ambassadors to civilizations we can only imagine. The images returned by spacecraft have fundamentally altered human perspective on our place in the cosmos. The pale blue dot photograph showing Earth as a tiny speck suspended in a sunbeam highlighted both our cosmic insignificance and the precious uniqueness of our world. These views from space have inspired environmental awareness and a sense of global unity that transcends national boundaries, reminding us that national borders are invisible from space and that we all share this small oasis in the vast darkness. Modern spacecraft missions increasingly involve international collaboration, bringing together former adversaries in pursuit of common scientific goals. The International Space Station represents perhaps the finest example where astronauts and cosmonauts from around the world work together daily, pushing the boundaries of human knowledge and capability. These partnerships demonstrate that our greatest achievements often come when we set aside political differences and work towards shared objectives. The economic spin-offs from spacecraft technology permeate modern life in ways most people never realize. Miniaturized electronics, advanced materials, life support systems, and countless other innovations driven by the extreme requirements of space exploration find applications in everything from smartphones to medical devices to transportation systems. The global positioning system that guides everything from ride-sharing apps to precision agriculture grew out of navigation satellites that themselves descended from early space exploration efforts. Educational outreach has become an integral part of spacecraft missions, with rovers named by schoolchildren and images shared instantly with classrooms around the world. These missions serve as powerful tools for inspiring the next generation of scientists, engineers, and explorers. Children who watch rovers explore Mars or see images of distant galaxies may be motivated to pursue careers that will carry humanity's exploration efforts even further into the future. The philosophical implications of spacecraft exploration extend far beyond scientific discovery to fundamental questions about humanity's destiny. As a species, these mechanical emissaries represent our first tentative steps toward becoming a truly spacefaring civilization capable of spreading life and consciousness beyond the confines of a single world. Whether driven by scientific curiosity, resource needs, or simple wanderlust, the urge to explore seems deeply embedded in human nature. Spacecraft serve as time capsules preserving human achievement for future generations. The lunar modules left on the Moon by Apollo missions will remain there for millions of years, serving as monuments to human ingenuity and courage. The plaques and instruments deposited by Mars landers will someday be archaeological artifacts for future explorers, whether human or robotic, telling the story of our species' first attempts to understand worlds beyond our own. The loneliness of spacecraft traveling through the vast emptiness between worlds mirrors humanity's own isolation in the cosmic dark. Yet these solitary explorers carry with them our collective spirit, our curiosity, our determination to understand, and our hope that somewhere in the universe we might find kindred spirits, or at least answers to the deepest questions about existence itself. As we follow these mechanical pilgrims on their patient journeys across the solar system and beyond, we're reminded that exploration is not always about dramatic discoveries or heroic adventures. Sometimes the greatest achievements unfold quietly over years and decades through the steady accumulation of knowledge, the persistent application of scientific principles, and the unwavering commitment to push just a little further into the unknown. The story of how spacecraft travel through space ultimately becomes a story about us, about our refusal to be confined by the apparent limitations of our biology, our determination to extend our senses across impossible distances, and our faith that the universe holds secrets worth discovering, even if those discoveries require decades of patient work and the investment of our finest minds and resources. In the gentle drift of these mechanical explorers through the cosmic dark, we see reflected our own deepest aspirations, the desire to understand our place in the universe, the hope that we are not alone, and the conviction that knowledge itself is worth pursuing, even when the practical benefits may not be realized for generations. Like the spacecraft themselves, we are travelers through space and time, seeking meaning and connection in the vast expanse of existence. And so, dear traveler, as we reach the end of our gentle journey through the mechanics of space exploration, we find ourselves contemplating something quite wonderful: the realization that every spacecraft mission, whether it whispers through the void on ion winds or thunders away from Earth on pillars of fire, represents humanity's quiet rebellion against the constraints of our earthbound existence. These mechanical ambassadors carry with them not just instruments and cameras, but something far more precious: our collective curiosity and our refusal to accept that the horizon marks the limit of what we can know. The mathematics that govern spacecraft trajectories may seem cold and precise, but they describe something profoundly beautiful. The way objects dance through gravitational fields following paths carved by invisible forces older than our sun. The elegant curves traced by spacecraft as they swing past planets, gaining energy from cosmic encounters that were planned years in advance by minds that dared to imagine touching worlds they would never see. These trajectories become poetry, written in the language of physics across the vast canvas of space. Consider for a moment the extraordinary patience required for these endeavors. When engineers design a mission to Jupiter or Saturn, they must think not in terms of weeks or months, but years and decades, trusting that systems built today will function flawlessly in environments that would destroy any living thing almost instantly. This faith in engineering and physics represents one of humanity's most optimistic acts: the belief that careful thought and precise construction can overcome the seemingly impossible challenges of the cosmic environment. The spacecraft, currently making their way through our solar system and beyond, carry within their circuits and sensors the accumulated wisdom of generations of dreamers and builders, from the ancient astronomers who first mapped the movements of planets, to the rocket pioneers who proved that humans could indeed slip the surly bonds of Earth, to the modern mission planners who orchestrate these intricate celestial ballets. Each mission builds upon the achievements of those who came before, creating an unbroken chain of exploration and discovery. There's something deeply moving about the way these mechanical explorers continue their patient work long after their original missions have ended. The Voyager spacecraft launched when disco was popular and personal computers were science fiction, continue to transmit data from the edge of interstellar space, their plutonium hearts beating steadily as they have for nearly half a century, carrying messages from a younger humanity into the cosmic deep like bottles cast into an infinite ocean. The images they send back transform our understanding, not just of distant worlds, but of ourselves. The swirling storms of Jupiter, the delicate rings of Saturn, the rusty canyons of Mars, and the icy geysers of Enceladus. Each discovery adds another verse to the grand poem of planetary science, while simultaneously reminding us of the extraordinary rarity and preciousness of our own blue marble suspended in the darkness. Perhaps most remarkably, these missions reveal the power of international cooperation. In pursuit of knowledge, spacecraft components built in different countries by teams speaking different languages come together to create instruments of discovery that transcend national boundaries when data arrives from Mars or Saturn. It belongs not to any single nation, but to all humanity, adding to our collective understanding of the universe we inhabit. The technologies developed for spacecraft often find their way into everyday life, improving medical devices, creating new materials, and advancing our understanding of complex systems in ways that benefit everyone on Earth. The miniaturized electronics that allow a rover to analyze Martian soil samples also power the smartphones in our pockets, while the life support systems that keep astronauts alive in space contribute to better air filtration and water purification systems here on Earth. But beyond the practical benefits, these missions serve a deeper purpose. They remind us that we are explorers by nature, that curiosity and wonder are not luxuries, but fundamental aspects of what makes us human. When children watch a rover take its first steps on Mars, or see images of galaxies billions of light years away, they glimpse possibilities that may shape their entire lives, inspiring some to become the engineers and scientists who will carry exploration even further. The gentle persistence of spacecraft navigation teaches us something valuable about achieving ambitious goals. The success often comes not from dramatic gestures, but from patient, consistent effort, applied over long periods of time. The ion engines that push spacecraft across billions of kilometers produce thrust so gentle you could barely feel it. Yet their whispered acceleration accumulates over months and years into velocities that chemical rockets could never achieve. This principle applies far beyond space exploration in our own lives. The most meaningful achievements often result from small, consistent actions rather than grand dramatic efforts. Just as spacecraft must sometimes slow down to speed up, or take longer paths to reach their destinations more efficiently, we too sometimes discover that the indirect approach proves more effective than the obvious one. The loneliness of spacecraft traveling through the vast emptiness between worlds reflects something profound about the human condition. We too are isolated travelers moving through space and time on our small world. Yet like those mechanical explorers, we carry with us the hopes, dreams, and accumulated wisdom of all who came before us. And like them, we have the power to send messages across the void, connecting with others who share our curiosity about the universe. As these patient explorers continue their journeys through the solar system and beyond, they remind us that the greatest adventures often unfold quietly over years and decades, through careful observation, persistent questioning, and the gradual accumulation of understanding. They teach us that distance is no barrier to discovery, that time is not an obstacle but a tool, and that the universe rewards those who approach it with patience, respect, and wonder. The story of spacecraft navigation ultimately becomes a meditation on human aspiration and the power of ideas to transcend physical limitations. We may be bound by biology to a single world, but our minds and our mechanical extensions can travel anywhere, guided by the same physical laws that govern the dance of planets and the birth of stars. We are not separate from the cosmos, but part of it, temporary arrangements of matter and energy, capable of contemplating our own existence and reaching toward understanding. In the quiet hum of gyroscopes and the patient calculation of trajectories, in the gentle thrust of ion engines and the careful choreography of orbital mechanics, we find reflected our own deepest nature as beings who refuse to accept limits, who transform curiosity into knowledge, and who send pieces of ourselves across impossible distances in search of truth and beauty and connection. And so, as you drift gently towards sleep tonight, perhaps you can imagine yourself aboard one of these mechanical wanderers, gliding silently through the star-filled darkness, following ancient gravitational currents toward destinations that await discovery carried forward, not by fuel alone, but by the accumulated dreams and aspirations of everyone who ever looked up at the night sky and wondered what lay beyond. The spacecraft will continue their patient journeys long after we have gone, carrying our messages and our hopes into a future we can barely imagine. But in following their progress, in celebrating their discoveries, and in dreaming of the missions yet to come, we participate in something larger than ourselves, something that connects us across generations and across the vast expanse of space and time to the eternal human quest for understanding, sleep. Well, fellow traveler, and know that somewhere out there in the cosmic dark, our mechanical ambassadors continue their faithful watch, expanding the boundaries of human knowledge. One gentle thrust, one careful calculation, one precious image at a time, until perhaps someday they help us find our way to the stars themselves.